Actually, as Panos mentioned, I'm leading ultrafast laser micro nano processing group at FORTH in Greece, and we are actually, our expertise are focusing on laser materials processing, laser micro nano fabrication. But lately we have also worked on a lot on material science and how we can provide new materials and new, let's say, concepts in material science through the combination of ultrafast laser beams with the materials of the nanoscale. So in this context, actually, we have come up with how we can exploit the new, let's say, the new miracle materials that are emerging in the last few years, that are the metal halide perovskite nanocrystals. And these are actually very nice materials because they can fabricate it very in simple ways with typically solution-based processes. They can actually they can have a tunable band cap. You can see here that based on the synthesis protocol, one can obtain different shapes and sizes. Of course, there are some bigger disadvantages of these perovskite nanostructures that are chemical and structurally unstable, especially under moisture conditions. But still, I mean, it's a very nice family of materials that can be explored for many applications, including energy storage applications. And I will try in this actually lecture to present our initial work on this and preliminary results on this direction. So this is the general chemical formula of the metal halide perovskite nanocrystals of the ABX3, and you can see that the different components of these perovskite structures. And what we have actually, what is actually very nice with this is that it can be classified based on the crystal structure and size on the different dimensionality crystals. For example, the first one is a 3D structure, the ABX3 structure, and this is when the cation A fits the cavities of the organic lattice upon ABX stoichiometry, and then a stable 3D perovskite structure is formed. However, when the A cations are quite large, then the crystal structure includes layers of corner sharing octahedra. You can see here this case. And in this case, we have two-dimensional structures which are characterized. So we have layers of this octahedra that are separated with other layers. And in this case, we have this formula, this A2BX4 formula, or the two-dimensional structure of these nanocrystals. And again, when we have the lead halide framework consists of octahedra that are connected at the corners or faces, then we have a chain of this octahedra or one-dimensional structure. And finally, the zero-dimensional structure is that this structure behaves as it. We have isolated BX6 octahedra. You can see it here in the blue octahedra that are fully surrounded by A cations, the green cations. So in this case, we are talking about the zero-dimensional structure. So how these materials are suitable for energy storage applications, and especially for lithium batteries. This is the question we had at that time, back to, let's say, to 3 years ago. So we have considered of this perovskite-based anode for lithium-ion batteries. You can see here an architecture of the cell. We have indium tin oxide that is conductive electrode, and the perovskite layer on the top of this electrode as an anode that will be used as an anode. And then we have the aqueous electrolyte. We need the requirements we need to have here is that in order to protect the perovskites, because they are very sensitive, especially to aqueous electrolytes, we need a passivation layer that will protect the perovskite structure by the water attack of the aqueous electrolyte. And then we have the cell is completed with a cathode. And of course, the requirements for this kind of cells, of energy storage cells, is that we have to, of course, to use a low-cost fabrication in order to be viable for potential applications, and also, of course, to use a non-flammable or an aqueous electrolyte. And apart from the low-cost fabrication, the whole process, from the synthesis of materials to the synthesis of the passivation layer, should be low-cost and scalable processes. So the first system we have actually worked on is actually Nancy Kostopoulou, that is a postdoc in my lab, has worked in this direction. She has produced zero-dimensional nanohexagons through colloidal synthesis, which and through a room temperature process. This is very nice about the formation of these nanohexagons. They can be easily formed at the room temperature. And actually, this is the structure you can see here. There are some inclusions of the three-dimensional phase in this zero-dimensional nanocrystals, as you can see in this TEM image, and also on the X-ray diffraction measurements. And the second one is a three-dimensional structure of nanocrystals. These are microcubes, and these are very easily, again, formed in room temperature through a cost-effective and solution-based method. You can see here the precursors spreading on the substrate. So this actually, the formation of these crystals are occurring on a substrate itself through a process, and this is actually a ligand-free. Throughout this process, the crystals we are producing that are microcubes are ligand-free, and they are nucleate and grow on the top of the substrate itself. So we have a direct growth in ambient conditions of these microcrystals, microcubes. Now, this is regarding the material of the anode itself, the active material. Then, of course, we need a good passivation layer, an appropriate passivation layer that can be permeable in lithium ions, but at the same time should be impermeable to the electrolytes. So this is actually, at that time, we have realized that the pulse laser deposition is a good candidate in order to obtain this kind of layer, and we have come up, of course, through the literature search and many studies, theoretical studies, that a shielding layer of titanium dioxide should be quite, let's say, effective and quite reasonable to have. So why pulse laser deposition? It's an easy technique that can be easily obtained. It can be used to obtain multi-component film that is of the desired stoichiometric ratio. So this is one advantage of this technique. It has a high deposition rate, short test period, and low substrate temperature requirements. And films that are prepared are quite uniform. And it's, of course, it's simply is not, let's say, quite expensive, and it has the potential of scalability. So we have applied this technique, and as you can see here, this is the first approach to obtain electrochemical cells using these nanohexagons. These nanohexagons were drop casted on the top of indium tin oxide, and then, as you can see here with the PLD, we have deposited the titanium oxide layer. And then, actually, in order to improve the integrity of the cathode, of the anode, we have applied an annealing process. So you can see here there is this is the non-annealed case, or this. You can see that there are these particles, these nanohexagons are separated, and you can see that the average size of this nanohexagons is about 100 nanometers. This is size distribution, and then the size of the particles. And then upon further annealing, you can see on the anode larger and larger grains. You can go to 170 in the 3 annealed process, and then in the 5 annealed process, you can see that you can this agglomerated. These nanohexagons are agglomerated and can reach up to 200 nanometers. So this actually we have measured the electrochemical performance of these layers against the silver chloride electrodes, and you can see here that in the non-annealed case we see practically no, not let's say electrochemical activity in the cyclic voltammetry experiments. By the way, the cyclic voltammetry characterization has been done by Dr. Bernardo in the Hellenic Mediterranean University. But when one anneals and you can see larger grains, one can see electrochemical performance, and then in the 5 annealed case, you can reach a capacity of 377 milliampere per gram. And this is repetitive and can last up to 100 scans, and then the cell degrades. So because we have possibly, let's say, degradation of the passivation layer. We have published this back to 2019. And the second system actually, that's the ligand-free microcubes via direct growth. You can see here again that the current density versus potential characteristics. And you can see that in this case, the capacity can reach up to 549 milliampere per gram. And the stability is much more, let's say, much more improved in this case. It can last, this cell can last actually up to 1,500 scans. So this is actually how this approach compares with other, let's say, perovskite structures. Mostly, most of the structures that have been used in the past are hybrid organic and inorganic metal halides. Our approach is based only on all inorganic metal halides, and you can see here that our results are pretty much actually very close to the performance of the hybrid organic and inorganic metal halides as far as the capacity. So are close, very close, but actually the stability in our case, especially in the case of the three-dimensional structure, the stability that is shown here in the cycles, as far as the cycles is concerned, is much better in the case of all inorganic metal halides compared to the hybrid organic inorganic halides. And the point here is that the fabrication process is room temperature. So we have we need no annealing steps, especially in the case of the microcubes, and actually this reduces the cost of the fabrication of these lithium batteries anode. Now, then we have actually come up to the question, of course, how this performance can be further improved. And this is actually what we had in mind at that time, that of course we may, because we have seen this annealing effect in the nanohexagons, that we may have some issues related to the conductivity of the percolation of the lithium ions within the anode, and how we can improve the electron conductivity in the anode itself. So at that time, I mean, in the literature, what people have employed in order to increase the electron conductivity among these nanocrystals, or among the different components of the anode electrode, they have used the carbon black as a binder, or PVDF, that is a polymeric conductive polymer that is used in order to improve the percolation of electrons between the or among the different nanocrystals. And we thought that this might be a very good, let's say, solution, and we thought about a solution process conductive material that can be used as a binder. And at that time, you have worked on the reduced graphene oxide, so how we can conjugate the perovskite nanocrystals with reduced graphene oxide flakes in order to enhance the percolation of electrons among the nanocrystals. So We have actually came back to a previous method we have developed in the lab, that is actually the conjugation of nanoparticles with two-dimensional materials, and it's a very simple approach. We use a femtosecond laser source. This is a quartz cell. When the nanocrystals, the perovskite nanocrystals, are diluted together with reduced graphene oxide flakes, and then we irradiate different conditions this mixture of materials, and then upon tuning the conditions, that is the irradiation time, or let's say the laser energy, and also the environment, I mean the solvent of the different of the nanocrystals or the RGO, then actually we this is actually our old results that are related to conjugation of gold nanocrystals on two-dimensional nanosheets. This is the case of gold immobilization of gold nanoparticles on graphene oxide, and this is the case of tungsten disulfide. But then we have applied this on metal halide perovskite nanocrystals. That is actually an unexplored area. There are some, of course, there is a limited knowledge, but there are some, of course, works there related to the fragmentation of powder, anion exchange, and phase transformation. And also these are the materials that have been used to date. To cut a long story short, we have performed this experiment. We have, let's say, fabricated reduced graphene oxide conjugates with perovskite nanocrystals. This is a very simple process, a solution. These are the laser radiation parameters we have used. And these are the results. You can see in the case of the, in the case of the nanohexagons, and you can see here the different, let's say, how the structures, this conjugation is evolved upon increasing the number of pulses at a specific fluence. And also you can see here how the photoluminescence is evolving. We can see, of course, the conjugation of the particles with the flakes through the corresponding photoluminescence sequencing due to this conjugation. And this is the results in 513 for this phase with the graphene oxide, but we have also managed to, with this three-dimensional phase, to conjugate these cubes, these nanocubes, with the graphene oxide flakes. And of course, here you can play with wavelength, with the type of perovskite nanocrystals, the 2D material, the solvents. So this general method of conjugation that can be done with it in this way. And these are the first preliminary results. And so we have a lot of actually work to do in order to prove that this is a very nice concept for the preparation of conjugated perovskite two-dimensional materials, anode materials for batteries. And you can see here the just a comparison. You can see here the perovskite with the titanium dioxide layer alone. You can see that we have more than one order, more than three orders of magnitude increase in capacitance when one is using perovskites compared to RGO itself, with the titanium dioxide layer, of course. But then if we are using this combination of the conjugated perovskite nanocrystals with titanium dioxide, then you can see to have an improvement by more than one order of magnitude of the capacitance of this anode. And this is quite encouraging results. Of course, we are working on this. These are preliminary results, and unpublished, of course. Unpublished, of course. And then, and I'm finishing with this. We actually, what we are doing right now is not on to work on the other side of the cell, on the cathode. And this is actually, we according to recent studies and recent review articles by flagging, it's the texturing of the cathode is in the fabrication of a 3D cathode, of a three-dimensional cathode, is a quite, let's say, attractive concept for energy storage applications, because actually the 3D texturing of the the cathode leads to an increased active surface area, and of course increased capacitance of the cell, and also this texturing improves the electrode, sorry about this typo, the electrode wetting and with the electrolyte. So in a sense, if we have a textured electrode, then we can have let's say a very low contact angle with the electrolyte, and in this case to enhance the lithium ion transport. So we have worked with commercially available cathodes that are used in this kind of cells. You can see here a structure of these cathodes. These are lithium iron phosphate cathode that this is the collecting electrode. It's about 60 nanometers or 70 nanometers, the thickness of this cathode. And these are the first results of texturing of the using femtosecond laser of these cathodes, of the LFP cathodes as they call. And you can see here that we can pretty well structure through an ablative process, and you can reach back to aluminum collecting electrode. And all texture cathodes showed a superphilic behavior with the electrolyte that is used in this kind of batteries. And this is quite sorry, this is not so. This is not. It is too many. So it's too much. So it should be 463. So all texture cathodes become superphilic with electrolyte, and this is encouraging because then we can continue working in this direction and check whether through this texturing process we can increase the capacity, the capacitance of this cathode, of this cell. So I'm finishing with that knowledge funding through European Union proposals, funding, and also national funding, together of course with Laserlab-Europe. And let me acknowledge the contributors. I mentioned Nancy Kostopoul, that did all the synthesis of perovskite nanocrystals, and Dr. Bernardo did all the electrochemical cyclic voltammetry measurements, and of course people from the lab, from both labs in the ULM in FORTH actually, and the Hellenic Mediterranean University. And with this, I would like to thank you for your attention.